Good day, folks. This is tutorial number 15 in a playlist which is really intended for people who want to see how 3D Experience's FEA solver relate to the ABAQUS program. In fact, buried in the 3D Experience, it is the ABAQUS finite element solver. Now, this is tutorial 15. In tutorial 14, I more or less did the same type of problem, except that it was not a round sample, it was a planar sample, and the damage model that was used was ductile damage. In this tutorial, I will be using a round sample and the Johnson-Cook damage model. And the calculation is going to be done with the explicit solver. Now, what I usually do in these playlists, in this playlist, for transitional purposes, is look at someone who has done this problem with the ABAQUS program in a step-by-step fashion that is actually available on YouTube. And then we replicate those steps as it pertains to the 3D Experiences FEA solver, which is ABAQUS buried in it. So this particular problem is actually done with the ABAQUS program with the link below, and I'm going to replicate those steps. The material that we're using is steel, so these are standard properties of steel, density of the steel, Young's modulus and Poisson ratio. And I've taken snapshots of the screen from that same reference that I showed you. So for the plasticity model, he's using Johnson-Cook, and these are the parameters that are needed in order to input. Please note that in these tutorials, I'm not evaluating the validity of what was done in the original reference. I'm just replicating the steps. Therefore, if you need to know more about Johnson-Cook model or what these parameters are, you really should go to a reasonable reference, which definitely is not going to be an elementary reference, and check it out or search it on internet. Now, when it comes to damage model with Johnson-Cook, there are 5 other parameters that are going to be listed like that, and these last 3 are also included. And then you have to discuss the evolution of the damage, and the evolution of the damage in that reference is based on displacement at failure, which is 0.44 millimeter. Correct. So again, the snapshots, the screenshots were taken from that reference. Now, let me show you how we're going to go through this thing in a step-by-step way, but I want to show you how you define the material property in 3D Experience. You define the density, there we are. You define the Young's modulus, elasticity, elastic Young's modulus Poisson ratio. Then you go to the plasticity, and you select from the pull-down menu, you select the Johnson-Cook, and you put these numbers in it. These are the same thing that I showed you a minute ago. Then you go to the Johnson-Cook damage. You go to the damage. Okay, this was plasticity up there in the previous slide, and this is damage. You put these numbers, and finally, damage evolution is the last one, which is 0.44 millimeter dimension. Now, we're going to create that model as a revolved object, and we need to partition based on the approach that the fellow at the YouTube reference has taken. I'm going to partition this thing using the idealization of the model and partition it so that it actually can be done with the hex elements. Okay. You're going to see that. And then we're going to mesh it. Because of the partition that we have done, this can be done entirely with hexahedral elements. and it's done here. And the reference, the mesh size, global mesh size is approximately 2 millimeter. Now remember, this 2 millimeter also affects as a characteristic length that the displacement of failure. So I'm assuming that the YouTube reference has already taken that 0.44 based on this reference element, reference size. We're going to change the element later on to the not the reduced integration but the full integration. We'll do that later. Then it's easy to forget the applying properties to the part. Now properties, the counterpart of it is in ABAQUS is called section. You have to apply sections, solve the section. And I'm going to create two groups, spatial groups, one all the nodes on the top, which is going to be pulled up by 28 millimeter, and a second group at the bottom, they're all going to be clamped. You can see that in order to do this, I have to have created a point up there, which ABAQUS calls it reference point, but I don't have to call it reference point, just an arbitrary point. And you create a coupling between that point and the group that I just created on the top. So this is on the coupling. And this point is going to be moved up by 28 millimeter. It's going to pull everything in that group by 28 millimeters rigid body. Now, when this is done, then we're going to go to the application which has the explicit solver in it, and that's mechanical scenario creation, explicit dynamics. And when you do that, automatically it's going to activate the nonlinear geometric effect. Okay. You can see that it's already checked. I didn't do that. It's checked automatically. And then we're going to do mass scaling. Otherwise, it'll take a long time. A long time. And for mass scaling, the same place that you selected explicit solver, use the pull-up menu, mass scaling. And these are this is the information that the YouTube reference has used, and we use exactly the same thing. Okay. And this once you look at the tree, you have this global element type assignment. You double click on it, this thing opens up. So I'm going to change it from reduced to the full integration to C3D8. And because we're going to be doing explicit analysis, you need an amplitude defined assigned to that translation. And in the tutorial 14, just like the fellow YouTuber does, just input this linearly varying amplitude, time versus amplitude. But it seems that this is not necessary. All you need is 2 points, 0, 0, 1, 1. Essentially, it replicates all of these things by interpolation. And that is taken from this reference. And this is where the damage takes place and the two pieces separate from each other. So let's go ahead and do that. Because this is a single part, I'm going to start with the part design. My units are all set properly, so on that vertical plane, I will sketch. I'm going to draw the cross section, and then we're going to shaft it or revolve it. So the first thing I'm going to do is I'm going to draw a line here. We'll go to maybe roughly, this is fine. We're going to dimension it in a minute. And then there, okay. So let me put a dimension, first of all, rough dimension from here to here. And I'm going to make that thing, I'll make it 70. So that makes my job easier when it comes to modeling this thing. And I'm going to dimension this. We're going to change that. We're going to change that later. It's not 70. So this is going to be 20. Okay, and this is going to be 15. That's the diameter on the top. Sorry, radius on the top. Okay, now we're going to draw the narrow section. The narrow section looks something like this. All right, and you'll see. Now I'm going to make a slight change here later on, but that's fine. So this thing is for now. Oh, this from here to here is going to be 6.25. Okay, and then there is a fillet here, and so I'm going to use a 3-point arc, and then we clean it up later. 3-point arc from here to there and to there. Except I want this thing to be tangent to that, so I select this, Control Add, and we make them tangent. Constraint defined in dialog box, and I'm going to make a tangent right there. And then this, what we need, remember that distance from the middle to that point is half of this, 64.39, half of it, okay? So let's go ahead and do this. So that distance, $64.39 divided by 2, okay? And that radius of that fillet is 10. Oh, let me delete this and then put a radius. Because with that constraint up there, you won't be able to specify the radius. So 10, good. So this is my sample, except that I'm going to mirror all of these things. So let me select all of these, including that. I'm going to mirror it. Mirror it with respect to that line. So there we are. And because I want to revolve this thing, one way of doing it, you can close this, or you can put an axis here. You can put an axis system right there, or an axis here, so that when you shaft it or revolve it, it's going to rotate about that. So exit, and then we're going to shaft it, automatically shafts it like that. Now, look, you can do this thing any way you want. It doesn't matter. Basically, I want those dimensions. That's all. All right, let's do a quick save here. And then we're going to apply. While I'm here, I'm going to create a point up there because later on we're going to use that as a reference point. So I create a point with the coordinates. Let's say make it 77. It looks like. Where is it? Maybe I'll make it 100. Yeah, good. So this is the reference point eventually that we're going to couple it with the nose on the top. Good. Now we're going to create our material. So we go to Tools, create a material. I'm going to call this thing tutorial 15. Tutorial 15. This is May 16, 2025. All right. And say OK. Just give it a minute. It's going to create a placeholder for that material, which we have to input the values. Okay, right here, tutorial 15. And we're going to say apply. We apply it to this. Make sure you click on the green check mark, and we're good. Notice that the material has been created, but there's no numbers in it. So we're going to close this. Okay, good. So let's go ahead and do that. Double click. Structural. Density. This was 7.8 e to the 9. 7.8 e to the minus 9. That's still 10, that is ton per millimeter cube. Okay, see that? Yeah. And then we say okay. Oh, don't say okay because there's more to do. Okay, then you go to the ABAQUS multiphysics, mechanical, elasticity, elastic. Okay, there we are. The Young's modulus is 210 MPa, 210,000 MPa. Poisson ratio is 0.3. Good. Then we go to plasticity, metal plasticity, plastic, use Johnson Cook. And those numbers you're going to put in there, the numbers that I had in the slides. And this one was 500. Next one is 800 megapascal. Next one is a power exponential 0.5. And next one is also an exponential 1. And these are melting temperature 1773. I don't think it uses these things, but well, we're not doing it well. That's okay. It's not we're not using these things, but I'll just follow exactly what the other YouTuber did. 293. Maybe it is actually it is actually internally used in the Johnson Cook model, probably. Okay, so let's see now. We go now to damage. Where's the damage? Damage. Uh, Not ductile. Well, ductile damage. That's fine. Ductile damage, but the Johnson Cook model, which is Johnson Cook right there, and this is where the other coefficients are going to go. And the first one was 0.05. Next one was 0.5. 0.5. Next one is minus 0.5. Oops. Should be minus 0.5. 0.5. Next one is negative 0.01. And this last one is 0. Yeah, that last one is 0. This is the same number that we input before, 1773 degrees Kelvin, and that fellow is 293. Okay, and this last number is 1. Now, just a comment that I have to make. Maybe at the beginning I said that we're not doing ductile damage. This is ductile damage, but the model that is being used is Johnson Cook. Okay, yeah, so that was a better way of putting it. Yeah, ductile metals. Let me okay. Let me rephrase it. We are doing ductile metal damage. Okay, but the one that was used in tutorial 14 was here, ductile damage, and you don't need the stuff. There's other things that you have to specify, but we are using ductile metals, and the damage model that we're using is the Johnson Cook. Okay, now if you expand this thing, there's another line here which is damage evolution, and this is where you put in your 0.44 millimeter. Okay, and I think that's pretty much it. Hopefully I didn't forget. Yeah. Okay, we have created our the model exactly like that YouTube reference does. Okay, now let me do a quick save here. So what we're going to do is we're going to go to structural model creation. This is where you do the meshing, but first we have to partition, of course. But you go to structural model creation, MTFEM model. All right, good. Now look here. There is we are in that module, structural model creation, but over here there is something that says idealization. If you use this pull-up menu, idealization, you have to select the piece, and that's what uh, this description is. You have to select the piece and then say OK. Good. Now you scroll to the right, there is a partition. You click on the partition. Okay. Volume to partition, let's take the whole thing. Now it says cutting element. We're going to cut it with a plane which is exactly 20 millimeters down from the top plane. So what I'm going to do is I'm going to create, I could have created these things before, but I can do it here too. Create a plane, offset from a plane, from this plane in the other direction, 20 millimeter. So it's going to cut it right there. Okay. All right. And do another one. It's going to cut it right there. There is a plane there, cut it. Or internally, you use a plane there, which is cut. Now, do another one. This bottom piece, another whatever is left here, whatever. And we create a plane, again, offset from a plane, from this plane, but not down there. We flip it, again, 20 millimeter. We say OK. And OK. So this piece, notice that it has been cut. This piece has been cut, and everything else is just there. You have to cut it there. Now, this is exactly what that YouTube reference does using the ABAQUS program. Okay, so we go to, and we have to exit this. Notice that this is what it's saying. Exit, exit. All right, now we go to measure. We want to do a partition mesh, partition X mesh. You select the part, it turns yellow. Now in the ABAQUS implementation of this problem, it became green, but that's okay. And we put down mesh size 2 millimeter and mesh it. There. Let me say okay. Right there. Okay. Very good. Don't forget to apply properties. This is what I said here. Do not forget to apply properties. So properties tab, solid section, you select anything you select, it's going to take the whole thing. It's going to take the whole part. And that's the material that I used, right? Johnson Cook, etc. Good. Let me do a quick save here. Now, while I'm here, I'm going to create the group of elements. So let me remind you how this is done. So under the group tab here, let me first put it in the view or front view, front. Okay. All right. So we're going to create a group, spatial group. Okay. Make a box like that. Make sure that everything but not the bottom nodes are selected. A little bit more. Yep. Turn it around. Make sure that things are selected on this side. So we have created a group of nodes up there. Eventually, it's going to get coupled to the top point. Good. So notice that the group has been created here. This is group 1, the top one. And we do exactly the same thing. It's easy if you go to the front view, move it up, zoom in, group, spatial group, make it. That's good. Make sure everything is selected. Very good. And yeah, here's the second group. See that? So we did create our groups, which was this. And now we create a coupling. Go back here. Under connections, there is a coupling right there. You click on it. Okay. So what do we need? Support 1, we need the top point, this point. Support 2, we go by groups. and that's group number 1, and it's a kinematic coupling, and that's pretty much it. So that's the top one. All right, we have created the coupling right there. You can see that there. Let me do a quick save and get out of here. So we're going to go to the mechanical scenario creation. This is where I have my Explicit solver there. If I go to the, for my role, if I go to, there's another one called structural scenario creation. Let me see if I can find it for you. Yeah, structural scenario creation. This does not have the Explicit solver, so I'm going to go there. Okay, I use the finite element model here that I created. Excellent. So for procedure, I go and select the explicit dynamics. Notice that later on I have to do masking. So select this. This pops up, but I told you by default geometric nonlinearity is included, which is good. So we did it. Then we are going to create a, let me see for a second, according to the slides here. So we are there, mass scaling. We're going to do mass scaling. Okay. Get the mass scaling thing. Yeah. So we go there, mass scaling. Now, if you look at this, slide, all right. Now that I answered the phone, I can go back to this. All right. So we go here and notice that first of all, uh, beginning of the step is what I have in that. Beginning of the step, right? The whole model, fine. Now I don't need this thing, just uncheck that, specify time increment, and then put down 1 e to the minus 4. 1 e to the minus 4. These are the same values that the YouTube colleague is using right there. See this? Everything there. All right, so let's go back, and then we say OK. Now, as for the type of element, here is the element type assignment. Double click on this thing. Default is reduced integration. You can change that thing to full integration. Excellent. Now we're going to apply the boundary condition. So we go to boundary condition. First of all, we clamp the bottom piece. So there is a clamp. We can do it by group, and that's going to be group number 2, the bottom piece. And then we apply a translation. Now notice that I'm going to show you something here. I'll show you that because I have to come back and do something else, something that I forgot to do, but on purpose I'm going to do it like that. So you go to apply translation, make sure that you don't miss it, because if you notice that you can miss it if you drag this thing sidebar up and down. But anyway, translation. Now, the support is that coupling, right? So the coupling we can select from the tree right there. And the magnitude is 28 millimeter in the Z direction, and say OK. Good. Now, when I run this thing, it's going to bomb out. Or if I actually update it, you see that there's going to be an error message. You see why. You see, it says you don't have an amplitude. That's the problem. Invalid amplitude. So we forgot to do the amplitude. I didn't forget. I just told you I have to come back here. So go to the setup, scroll to the right, general amplitude. I'm going to put down 0, 0, 1 and 1. So this is called general amplitude 1. Okay, fine. You can rename it the way you want, it doesn't matter. Now you update, you're not going to get that error message. Good, good. So you go to simulate, first do a check, model and scenario check. Double click on it. Yeah. That's what it is. That's what it's complaining. Okay, look. Let me run this thing again, see what happens. Okay. It says, look, basically you have in your applied translation, you forgot to do that. That's it. That's correct. Look, I created my amplitude, but when you go to the applied translation, it still says default. No. General amplitude 1. Now, if you update, no problem. If you run it, at least do a model check, no problem. Simulation check, no problem. And then we're going to run it. Just give it a minute. This is a simulation check. Notice that what I did, I created my amplitude, but in the apply translation, I forgot to select that amplitude. That's why it came back with that error message. So all I had to do was to go to apply translation, change it from default to the one that I created. While this is running, I want to tell you that in the 3D Experiences version of ABAQUS, what they have done, if you're using these damage models, it's going to show you separation. In the older version, you have to go and request output field, which involved the status. You have to check status in an output field. But it looks like that is not necessary anymore. Close that. This is fine. And now we're going to run it, and we're almost done. With the mask scaling, without the mask scaling, this is going to take a long time. But with mask scaling, it's pretty quick. And this is a true physical time, wall clock, okay? Just to show you how long it's going to take for it to run. Maybe a couple of minutes. If you click on the iterations tab, it will give you an idea of where you are as far as the total time is concerned. Total time is supposed to be 1, and it's marching. You can see that. 14% of the total time, 19%, 24. Yeah, my estimate of about two minutes was probably right. Once again, when you go to the ABAQUS reference, YouTube reference, you see that the fellow is asking for output request, including that status and things like that, which I did not have to do here. If you wanted to do that, there is a box here. It says output. Click on it, create an output request, and do ask for whatever you want. Because there are some preset and default information is going to spit out. If you want more than that, you have to go ask for it. This is almost done. Okay, extracting results. Good. Let me close this thing. This is the initial situation. Now you pull it. There, you can see that. That's where the necking takes place, and eventually it's separate. You can see this. Good. And it's in line with the numbers that this fellow is getting. But remember, we're not assessing accuracy here. Let me close this thing for a second. We can animate this thing. There's the animation. If it's too fast, you click on these three dot, and there's the clock, and choose the speed, and lower the speed to the place that you are happy. That's too slow. There. There we are. All right, folks. Good luck. That's pretty much it.